Hello everyone, welcome to my channel BW Audio Programming. Today I wanted to show you guys how to make this Polyphonic FM synthesizer. So this is going to be a pretty basic FM synth as far as the FM parameters, but we're going to go ahead and add a couple simple synth parameters as well so we can make this a full-fledged instrument. So it's polyphonic, meaning we can play multiple notes at a time. So let me show you what that's going to sound like. Right now I'm using my MIDI keyboard to control this too, but you can see them highlighted down here. So we're going to have some options to choose the carrier type as far as the carrier waveform. So we can choose between a sine wave, triangle wave, and a sawtooth wave. Then we'll have some options for the modulation frequency, a ratio dial, a detune dial for the ratio, and then, of course, a modulation index parameter. And then there'll also be an option to choose a free floating mode for the modulation frequency, so we can control that with this. And up at the top, you can see all the harmonics being displayed as well. Then, of course, we'll have an ADSR parameter. And a filter, with a few options for that. And then lastly, we'll have a little pitch wheel that can also be controlled with your MIDI keyboard, and a little stereo output mode as well. That will kind of liven up the instrument a bit. So anyways, that's going to be the goal. Now this is going to be a bit bigger project than my other videos, so I'll probably have to split this up into two. And the first one here is going to just focus on using the FM synthesis, or making that. And then on the second video, I'll go into how to turn this into a full synth instrument. So yeah, let's go ahead and get started. Cool, so as I said earlier, I'm going to start off just by making a simple FM synthesizer. And I'm going to do my best to explain a bit of what FM synthesis is and how it works. So what we're going to do is start by getting a couple cycle tilde objects, because for FM synthesis you're going to need two oscillators, because the way FM synthesis works is it stands for frequency modulation. And that is because what you are doing is using the output of one oscillator to control the frequency of another. And when you do that and you have this one coming at audio rate, that's what gives you those kind of crazy timbres that you get with FM synthesis. So we're going to start with that, and then I'm just going to get the dials we're going to need first of all. So we're going to need a frequency dial for the first oscillator, grab another one for this one. And another thing in FM synthesis is we give each of the oscillators a name based on their purpose. So the one that receives the frequency or the output of this oscillator is called the carrier, and then this one we call the modulator, which makes sense because it's modulating this one. So that's what those are called. And then let me just plug this into here. I'm just going to go ahead and get some output so we can hear a little bit, make sure that's all working. Grab a live.gain, easy DAC, plug that in, turn it down. Cool. So we have output. Now we just need to incorporate the second oscillator. So as I said, this oscillator is going to control the frequency of this one. However, we're going to need to add the output of this to our base frequency. That way this one still has meaning to us. So what I'm going to do is grab a sig tilde so we can convert this value into a signal. Then I'm going to grab an addition knob, addition tilde, plug that to there. This output goes here. That'll go into the frequency for the carrier. And then we just need to configure this frequency dial. Now if I turn this up, we should hear something. Exactly. However, we're not getting any effect from this modulator right now, and that's because it's only cycling between the values of -1 and 1, which is normally what you want for outputted audio. That's what this one is doing. However, for this one, we're going to need a larger range or give it a larger amplitude to have any effect on this carrier, because all this is doing is cycling between 509 and 511 hertz, so you're really not going to be able to hear that very well. So let's multiply this modulator by, let's say, 1,000 is a pretty decent number. There we go, so you can already hear that having an effect. And that's because now this is cycling between -1,000 and 1,000 at a rate of 390 hertz. So what we can do then is grab another multiplication object. Oops. Let me turn that off for a second. And then we'll grab another dial. And this one is going to be our modulation index. So if you've worked with FM synthesis before, you've probably seen modulation index as a parameter. And all that's doing is controlling the amplitude of the modulator. So I'm going to take the raw output from that, plug it into here. Actually, I'm just going to keep it at its regular value. And now this is going to control how much of this is coming through. So if I turn this up again, so when this is at 0, it's just a sine wave because this isn't having any effect on the carrier. But as I turn this up, actually let me grab a spectroscope so we can see what's going on. So there's our sine wave. As I turn this up, you'll see and hear the effect that the modulation is going to have. So as we increase that, we get a higher amplitude for the modulator, and that's what affects our carrier wave. And then as I change the frequency, you can kind of see how that's affecting the frequencies there. And one other thing I want to highlight for how FM synthesis works is kind of this pattern that comes around once you start increasing the modulation index. So if I move this to a range that we can see, I'm not going to turn it up because this is going to be ear piercing, but this kind of gives us a good way to see what's going on here. So when I have the modulation index at 0, this is just a sine wave, but as we turn that up, we start to see these sidebands come out. And these actually are related mathematically to a specific relationship between these two. So this center, most prominent harmonic right here, that's our main signal that we set for the carrier. But then each of these other sidebands is a distance of the modulation frequency away from the carrier frequency. So this one is 1,000 hertz plus 10,000, 2,000 hertz plus 10,000, 3,000, etc. And below it's 1,000 minus, 1,000 minus, so on and so forth. And as I increase the index, you can kind of see there's a pattern that comes out between those sidebands. First of all, you start to see more sidebands appearing, but actually if I increase this even more, you can see you start to get some crazy patterns. So at a certain point, this main carrier frequency starts to get less than the sidebands themselves. And that's because of a special relationship between them that's governed by what's called Bessel functions. It's some complicated like calculus that I don't really know about, but there is some mathematics that governs the effect that this is having. So anyways, that's just a little bit about how FM synthesis works. I'm going to turn this up again, turn this down, and actually you'll see as I turn this down, these lower harmonics, they'll actually flip in inverse once they hit 0. So you'll see them start increasing again as I move this carrier frequency down. So yeah, you can see that. And as I increase the modulation frequency, all of those start to separate more. Okay, so now the next thing I want to do is export this FM structure into a gen object. And that's because once we once we're going to start turning this into a full-fledged synth, specifically a polyphonic synth, we're going to want to turn that into an MC Gen object. And so it's just going to make our life a lot easier, and you'll see why later. So anyways, I'm just going to make a Gen object like that. If you've never worked with Gen before, I'll explain kind of what it is. It's a bit different than Max, but also relatively the same. It opens up a new patcher just like this, but the access to objects you have is a little bit different. And that's because in Gen, everything is a signal. So there's no like bang processes or anything like that. It's all just done at signal rate. So you don't need to specify a tilde for signals. Everything is just automatically like that. And that is because Gen allows you to access sample accurate buffers. So that way you can do things like sample delays and stuff like that. But anyways, so what we're going to want to do for this is just copy this exact structure we have here. It's similar to a patcher, so we're going to have some inlets. So I'm going to go ahead and just make a third inlet. That's going to be for our modulation parameter. And then what we want to do is grab a couple oscillators. So I'll copy that cycle. And our frequency is going to come in here. So we'll have to add that with the output of this cycle object. This is going to be the modulation frequency, and this is going to be the modulation index. So that's going to be multiply by 1,000. And then we take the output of that and multiply it with the output of the modulation oscillator. Send that to our output. And cool, now we have our Gen object. And actually, this was a lot easier to do in Gen than it was in regular Max MSP, just because you don't have to differentiate between the signals, but either way, it's relatively easy. So I'm going to go ahead and delete all this. I'm going to leave our parameters here. Carrier frequency there, modulation frequency there, and amount. So we'll send that out of Gen. And let's see. There's our carrier. Modulation, turn up the... Oh, that was pretty loud. Let me turn that down. Wait. That sounds like Taco Bell. This is probably exactly how they made that too, I'm sure. Sounds exactly like Taco Bell. Okay. Anyways, there we go. We have our Gen object. You can see all our parameters still work, although it is really loud, and I think it's because I put this value a little too high. So I'm going to change this back to just multiply by 100. There we go. And this is a less harsh of a range for that. But you can make that higher if you want to. It's up to the programmer's choice. So there we go. Now we have our Gen object. Pretty simple. If all you wanted to see was FM, then that's pretty much it. But we are going to add a couple more parameters to this. So the next thing I want to do is, if you saw with our original example, we had that ratio dial. And what that is going to do is basically allow us to set the modulator frequency as a ratio of the carrier frequency. So to do that, I'm going to go ahead and just make a new dial. Doesn't really matter. I'm going to customize this one. So we're going to call this the ratio. And we want this to not be a free floating value because we want it to sync to specific integers and half integers that give us more harmonic results from the FM synthesis. So what I'm going to do is change the range from 0.5 to 10. And I would like this to jump up by increments of half. So the way we can control that is if you go to the steps parameter towards the bottom, there you can specify how many steps you want within your dial range. So since we want to go up by half increments from half to 10, it's 2 times 10, which is going to be 20. So there's that, and then I'm just going to get rid of that percentage, make it a float, and let's see. Perfect. So now you can see that this jumps up only by half increments. So that's going to be the dial there. Now what we need to do is send this into our gen object and then do the little bit of arithmetic with it. So let's go into gen. I'm going to grab another inlet. Call this inlet 4, although I actually want to switch this, that way we keep our two inlets together. So I'm going to make inlet 4 the modulation index, and then inlet 3 will be the ratio. So let's switch these around, put that into here, send our ratio in. And now the ratio is going to be a ratio based off the carrier frequency, which is coming in over in our first inlet. So all we need to do is grab a multiply object. Carrier frequency will come into that. Multiply it by our ratio. And then what we need to do is we need to set up the logic for selecting between the two. Because if you saw in the original example, I had what's called a live.tab. Let's go ahead and make that right now. And that's like a radio group that will allow you to select between a few options. And it's going to output just an index like this, 0, 1, and 2. But we're going to change that because we only need 2 options. So if you go into the inspector, go to the range enum. That's where you can rename and select the range. So I'm just going to type ratio and free. Free mode is what we're going to call just the non-ratio mode. And that's going to be it for that. Now it's sending out 0 and 1. And if we go into gen, the object that we're going to use to select between these is actually called selector. And that takes an argument, which is going to specify how many inputs you have. We're going to have 2. And basically using another value to select between the two, it'll send either one of those out or one of those inputs through the outlet. So let's get rid of this. That's going to be the free dial. Actually, I'm going to switch these around. So here's going to be the ratio control. That'll go into the second inlet, and the free control. That'll go into the third. And then we need to grab another inlet, and that is going to be for that radio group we created. So that'll come over here, come to the selecting portion for the selector, and that will go into the frequency inlet for our cycle object. So if we get rid of that, one quick thing we need to do for this is selector is so expecting values either 1 or 2 for either of these. So we simply need to add 1 to the output of this, and that will give us a 1 and a 2. Perfect. If I send that in there, initialize it a little bit, now we should be able to hear the difference. Let's see. I'll turn up the modulation index. So if I turn up the ratio dial, you can hear how that skips to different portions. And this is nice because hopefully you can hear these integer frequencies give us a bit more harmonic of results, whereas if you go to free, a lot of those in-between values are kind of not useful, and especially once we get the MIDI functionality involved, those will kind of not adjust the way we want them to, but more on that later. So anyways, that's the basic controls for that. Now there's one last piece of functionality I want to add to this, and that's changing what our carrier waveform type is going to be. And this isn't an effect I see a lot with FM synthesis, but I think it's kind of interesting and you can get some different sounds out of it, so we're going to add it for this. So it's going to be similar to what we did with the ratio and free dial, where we have a live.tab to control it. but the three waveform types we're going to use for this are going to be, those are going to be sine wave, triangle wave, and sawtooth wave. So I'm going to make that like there. And now if we go into the gen object again, may as well just make another inlet for that right now. So what we're going to be doing is right now our carrier wave is just a sine wave specified by the cycle object. But we have a couple options for different waveforms in Max. So I'm going to try choosing those instead of the sine wave. And the first one is going to be triangle. That'll create that. And the second will be a sawtooth wave, which we actually call phaser. And there's something a little tricky that's going to happen here. So both the cycle and the phaser objects, their inlets are the wave frequency. So you just specify the frequency, and that gives you the waveform at that frequency in the output. However, the triangle wave specifies a phase. And what that means is you can actually cycle through the waveform by giving it a ramp value. And the way you do that is we basically want to generate a ramp signal. And the perfect thing we have for that is actually right here is our phaser. So the reason they call this a phaser and not a sawtooth wave is because it's used for powering things like a triangle wave and other wavetable oscillators. But at the same time, it's also just a sawtooth wave. So what we can do is we're going to send the phaser into the triangle, and that's going to power that. And then we'll take this frequency, plug it into the phaser. Now, whenever we specify a frequency here, this phaser is going to create that up ramp at that frequency, and that is what's going to power the triangle. So we're going to get the same frequency from the triangle as well. And so what we need to do now is grab another one of these selector objects so we can choose between them. Say selector 3, so we get those inlets. This one is going to be the index, and then our first option will be sine, second will be triangle, and then we can just grab this phaser from right here. We don't need to create another one because we can just kind of daisy chain off that. So we're going to do that, go to the output, and that should be it. Oh, we just got to plug this in and add 1. So let's see if that's going to work. I'm going to turn off the modulation right now. Turn this up. There we go. Had to initialize it. So there's a sine, there's a triangle, and there's our saw. So let's see how that sounds with some of the modulation index. You can hear that that gets a lot harsher than the sine wave does, and that's because it's actually going to generate sidebands for each one of these frequencies. So if I turn this off, this is the harmonic series for the triangle wave alone, just a regular triangle wave. And so once we do FM synthesis onto that, earlier when I showed you how each of these or how the carrier wave had sidebands for that, now each one of these harmonics is actually going to generate its own set of sidebands, which is why it gets very harsh when you do FM synthesis with different waves like this, but you can still get some interesting sounds, so I like to include it anyway. So let's see how that sounds. Yeah, that's pretty harsh. Sounds a bit better with ratio. And the saw wave, you can hear that's really harsh, even if we go to a low value. But cool. So I just took a second to clean that up a little bit. Now that's all we're going to do for the FM synthesis parameters. If you're only interested in seeing how to do FM in Max, then that's pretty much going to be it for that. But hopefully you got some good ideas of how you could branch off this, add some more ideas of your own, and kind of play around with it a little bit. But the next thing I'm going to do is start getting some MIDI control into this patch. So first thing I want to do, you can't see it, but I have my MIDI controller over here. And so I'm going to start incorporating getting data from the MIDI controller. And the first thing you want to grab is an object called MIDI in. pretty simple. It pretty much says what it does. It gets MIDI in, and you can specify what MIDI controller you're using by double clicking on it. I'm using this one right here. And then the most useful object whenever you're doing MIDI stuff is called MIDI parse. Because when you get output from the MIDI in, it simply gives you raw MIDI data that looks like this. Oh, well, you can't tell, but you actually get it in like a broken list. Let me print that out. Probably can't see it, but every time I hit a note, you get 3 individual messages that are all grouped as one MIDI message. But you don't want to deal with that on your own, so instead we grab this object called MIDI parse, and that basically breaks that up into the various MIDI messages you're going to have, like note on, poly key pressure, control changes, pitch bend is one of them, and yeah. But all we're going to deal with right now is this first outlet, which is note on and off pitch and velocity. So if we send that into this message box, right now I'm just going to hit the C note. So this tells us that this is MIDI note 60, and it's being hit with a velocity of 122. And if I hit a little lighter, now we get velocity of 21. But we're not going to deal with velocity right now, so I'm just going to unpack that list. And now from this left outlet, we're just going to get the MIDI note number. And that's what we're going to use to get the frequency to go into our carrier. So what we're going to use for that is an object called MTOF. It stands for MIDI to frequency. And here's our MIDI. And now here is our frequency. So this is how we get the frequency values from a MIDI controller. And this is going to be what goes into this carrier dial right here. And we want to make sure that this is going to the carrier dial, not the modulator, because the carrier is the frequency that's going to dominate the actual pitch, whereas the modulator just affects all the sidebands that are being created with the modulation. So I'm going to go ahead and plug this into our carrier, and that should give us a good start. Let's see. I'm going to play a few notes over here. Cool. So you can hear that's working. That's all you had to do if you just want to get frequency input. But it's not really a full-fledged synth, because as you know, a synth, like, there's no amplitude control at the moment. All I can do is change the pitch. But there's not going to be any shape to that as far as the amplitude is concerned. But what I want to do next, just in case you don't have a MIDI keyboard controller with you, is I'm just going to add what's called a K slider. And that is how you get this on-screen keyboard here. And this basically just sends out MIDI messages, just like a regular MIDI controller would, but only the note value and the velocity. So the way we're going to do this is, I'm actually going to delete the MIDI parse from this. I'm going to delete this from there. Then we're going to take this MIDI note number, send it into the K slider. And now when I play a MIDI note, you can see that highlights it as well. So this way you can either play your MIDI controller or just use the on-screen keyboard, and then that is going to be sent out to the MTOF. So let me turn that up again, make sure it's working. Perfect. So that'll be useful if you don't have a MIDI key controller on hand. Oh, and so right now, this quick tip, this is kind of in the way. If you just press U on your keyboard, that'll send patch cables behind your actual objects, which I always do that first thing in Max, just because it always gets annoying. So there's a quick tip there. Okay, now the last thing I want to do for this video, something I forgot to do earlier, is add this Detune knob to the ratio. So if you remember at the beginning, we had this Detune knob right here that could control how much we detune the ratio value from. So I'm going to go ahead and do that before I forget. And so I'm going to start by just making the dial itself, create a live.dial. I'm going to go into the inspector. There's no good prototype exactly for what I want, so we just have to customize it. First of all, I'm going to rename it to Detune. the range we're going to do is negative 50 to 50. And this is going to be in terms of percentage. And that actually should be it for that. So what we want to do with this dial is allow it to scale this value in case we do want it to be a bit inharmonic. So basically, if it's plus 50%, we'll add 50, and if it's less than 50%, we'll subtract 50. Although actually, now that I think about it, we should just make this 25 because it's kind of redundant to make it add 50 if you can already go to 5 plus 50. So I'm going to go ahead and change that real quick. So we'll do negative 25 and 25. That'll be a better range for us. Cool. So rather than implementing this within the gen object itself, I'm just going to implement it right here, because all we need to do is add the output of this to the ratio. So I'm going to grab a plus symbol, plus 1 dot, plug that in there, do that. Let's get a message box so we can see what's going on. So if I change that a little in this one, cool. So that's too high right now. Right now it's sending out 1.18, and we just want it to be 0.018. So that'll be easy. We divide by 100 decimal point, so it's a float. Plug that in there, and now let's see what's going on. Let's go up to 25%. Perfect. So now the value of 5.5 goes up to 5.75 when this is max, and down to 5.25. Perfect. But one thing you'll notice is that this doesn't output when we change the Detune knob. It only updates when we change the ratio, and that's because this is plugged into the left hot inlet, whereas this one is in the cold inlet. So we simply need to trigger this to update whenever we change the Detune knob, and we can do that really easily with an object called trigger. So trigger, you type it in like this, or there's a useful shorthand of just being T, so that's what I'm going to use. And this allows you to route an inlet into different types of outputs in a specific order. So the way I'm going to do this is type in B and F. B stands for bang and F stands for float, and the order of this is important. So the one you type in last is actually going to come out first out of the right inlet, and the one you type in first is going to come out of the left inlet. So first we want the float to happen, go through this process, and then be received in the cold inlet, and then it's going to send the bang out and update that value. So if I make that, plug it into here, I'll just show you with a couple message boxes. Whenever we change that, we'll get the float here and just a bang there, like that. And so the float will come into this, and then the bang will update that. So let's see. This should update now when I change the detune. Perfect. So that's the behavior we want. And whenever you encounter this problem in Max, which happens often honestly, trigger bang flow is usually the way to go. So cool. And yeah, so I think that's going to be it for this video. That's just the basic FM implementation done with a little bit of MIDI done. Now the next step is going to be changing everything to MC objects and dealing with the polyphony, because that's always the trickiest part whenever you're trying to make like a polyphonic synth in Max. So yeah, I hope you guys enjoyed this video. Stick around for part 2 if you want to see more. And yeah, thanks.